15, 16. All right, we're all here. So we're finishing up the review sheet today. So the next thing we're looking at is the rational zeros theorem. Rational zeros theorem. Do we want to look at 30 or 25 or 26? Which one of those two do we want to look at? 26? All right, guys, let's focus in. So rational zeros theorem is our P plus or minus P over Q. Plus or minus P over Q. P is the factors of the constant term. And in this case, our constant term is 15. We're not worried about the negative when we're looking at rational zeros. Here, we're just looking at the factors of 15. What factors of 15 are? 1 and 15. 2 is not a factor of 15. 3 is. 3 and 5. And that's it. Those are all the factors of our constant term, our factors of 15. Now Q, factors of the leading coefficient. Well,
I need the following students to report to room 10. Vince Menard, Shaylee Sellinger, Alan Tyson, and Taylor Tyson. Please report to room 10 at this time. Thank you.
if you want to stay, I will tell them that I forced you to stay. Yep. Yep. All right. Q is the first one. Q is leading coefficient. P is the factors of the constant. P is without a variable. Q is the leading coefficient, our one with the biggest exponent. Okay. So 12. We have 1 and 12. All right, guys, let's focus up here. So factors of Q is the factors of 12. So we have 1 and 12, 2 and 6, 3 and 4. Factors of P is 1 and 15, 3 and 5. Yes, P is our constant, Q is our leading coefficient. And when I list these out, I always start with the smallest value of Q and work my way up. Well, the smallest value of Q is 1. So we're going to divide all 4 values of P by 1. Well, 1 divided by 1 is 1. 3 divided by 1 is 3. 5 divided by 1 is 5. And 15 divided by 1 is 15. So with rational zeros, we will have all the factors of P relisted back out. 1, 3, 5, 15. Now we're going to move on to 2. So we're going to do 1 divided by 2, which is 1. P divided by Q. Every factor of P divided by every factor of Q. And to make sure that we have them all and none repeat, I just start with the smallest value of Q and just work my way up. Then we'd have 3 divided by 2, which is plus or minus 3/2. Now, I mean, we could do it in other ways, do each value of P divided by each value of Q and work it that way. But this here simplifies some, and we'll see it here in a little bit. Our next one would be 5 divided by 2, which is plus or minus 5/2. And lastly, 15 divided by 2 is plus or minus 15/2. Questions on what we've done for 1 and 2 values of Q? Let's look at 3. First one we're going to do is our plus or minus 1 over 3, which is plus or minus 1/3. Our next one would be plus or minus 3 over 3, or what is 3 over 3? Do we have it listed? We don't have to repeat it. 5 over 3, does that reduce? No, so we have plus or minus 5/3. And then the last one with 3, plus or minus 15 over 3, it reduces to 5. Now, if you're not sure on which ones reduce, which ones don't, 30xs, plug them in fractional form. If they reduce and it's repeated, don't put it down. If it doesn't reduce or is not repeated, put it down. All right, get another color. Because now we're moving to 4. So we'd have 1 over 4, so plus or minus 1/4. Then we'd have 3/4, and then 5/4 and 15/4. Now the reason I went on and just wrote those all back out because 1, 3, 5, and 15 do not have any common factors with 4, so there's no way they're going to reduce. There's no way that we'll have a repeated 1. 6. Well, we'll start with 1 over 6. Next one would be 3 over 6. Well, 3 and 6 have a common factor of 3, yes? So it reduces to 1/2. Do we have it? Next one would be 5 over 6. Does that reduce? No. So plus or minus 5/6. Our next one would be 15 over 6, which reduces to 5/3. And again, you don't have to have these reductions or reducing fractions memorized. Calculator will reduce them for you. Let the calculator do it if you do have issues or struggle with this, or you're not feeling comfortable or confident in reducing these fractions. Just plug them all in the calculator. I can do 16/5. 16 over, not 16/5. 15/5, and the calculator will tell me this here. Or we could say 15, I think it was 6 is what we're actually looking at, is 5/2. The calculator will do these for us. We don't have to do these in our head. Questions on this so far before we look at our last value of Q12? So again, we're going to start off with 1 over 12, which is plus or minus 1/12. 3 over 12 is 1/4. We have 1/4. 5 over 12 is plus or minus 5/12. And lastly, 15 over 12 reduces to 5/3. We do have it. So these here are all the rational zeros for this here. That's all we do. Incidentally, I did check this the other day, and it turns out that the zeros for the solution are none of the ones listed. This one here does not have a single rational zero. I just created the problem to find rational zeros. I didn't create it to be solvable. So I just picked random numbers as I went along, and then we worked it out. Questions on 25 and 26, finding the rational zeros. Do make sure you put the plus and minus in front of each one. Okay? Because you do need the plus and minus, because each one counts as a rational zero. 27 and 28, Descartes' rule of signs. We want to find the possible number of positive, negative, and complex zeros. Which one do we want to look at? 27. To find the number of positive zeros, we can just take the function as it is and count the number of sign changes. X to the 5th to X to the 4th, it goes from positive to negative, so that is 1. X to the 4th to X to the 3rd goes from negative to positive, so that's 2. Cubed to squared goes from positive to negative, so that's 3. X squared to X goes from negative to negative, so no, we did not have a sign change there. And from X to our constant term, it goes from negative to positive. So the number of possible positive solutions that we could have is 4, or an even number less than that. So if we wanted to list those out at this point, it would be 4, 2, 0. We would just keep subtracting 2. Does that make sense? Negatives. and we look at negatives, we're looking at f of negative x. And this can sometimes be a little confusing, a little challenging, but the main thing to focus on is we're replacing every x with negative x. The x to whatever power, so the first one, negative x to the fifth, is still going to have the x to the fifth. If that exponent is odd, it's going to cause the sign of whatever the number in front of it is to change from positive to negative or negative to positive. So just looking through this here, x to the fifth, x to the third, and our x, because negative 36x is really x to the first, these three are all odd, yes? So it means the sign in front of each one of those variables is going to change from negative to positive or positive to negative. And that's the key piece to this here. So our 6x to the fifth, if I plug the negative x in to find these negative solutions, it's going to go from positive to negative. Because when we plug that negative x in to x to the fifth, it's going to become negative x to the fifth. And when I multiply it by the 6, we get negative 6x to the fifth. I'm going to leave a space because according to the rule or the theorem for Descartes' rule of signs, the possible number of negative solutions is the number of sign changes of f of negative x. Now I'm going to leave a space, and y'all can watch this here and then fill it in all at once. But don't need that plus yet. 56x to the third. If I plug negative x in for that x to the third, it would be negative x to the third. So our negative times our positive is going to make it negative 56x to the third. And our negative 36, since it's an odd power, is going to cause that negative in front of the 36 to go from negative to positive. And well, the 40's sign doesn't change because there is no variable. We're not plugging anything into it. Even powers, as we've been taught or told time and time again, a negative times a negative is a positive. It works out any time we have an even number of negatives multiplied together. So multiplying them twice, 4 times, 6 times, 8 times, it will always work out to be positive. That negative is going to become positive. So what that's telling us is that negative x, when we plug it into x squared, that negative we plugged into it is going to be positive. Anytime we multiply a number by a positive, whatever the sign of the other number is stays put. So for our negative x squared, it's going to stay negative x squared. If there's an odd exponent, you change the sign. If there's an even exponent, it stays the same. And that's really what I was trying to get at originally. But that's all it's doing. We don't have to plug negative x in every single time and try to simplify. We can just look at the powers. X to the fifth told me it changes. X to the fourth stays the same. X to the third, change. X squared, keep it the same. X, change it. We don't do anything to the constant. Questions on this here? Count the sign changes. Fifth to the fourth, negative to negative. No. Fourth to the third is negative to negative. So no. Third to square. No. Squared to x. Our x to the constant. No. So the number of negatives that we can have is 1 or an even number less than that. But if we subtract 2 from 1, we get negative 1. We can't have a negative number of possible solutions. So we have this here. I think this is how this one worked out. I would have to look at more examples of that to tell for sure. But that is interesting. Now we set the table up. We always start off with the most of each, so 4 and 1, yes? And we already said we can't subtract anything from the negatives, yes? That means every single possible combination will have 1 negative. We can't have any less. 5, because the degree is 5. So in our first setup, if we have 4 positives and 1 negatives, we do have a total of, so we are missing none. So there's 0 complex, because again, the positive and negative should add up to be 5. If they don't, it means the ones that are missing are complex. And at this point here, I would subtract 2 from the negatives until I couldn't anymore, but we already can't. So I take 2 away from the positives. So we could have 2 positives, 1 negative, and 2 complex. Because if we have 2 positives and 1 negatives, that gives me a total of 3. We need a total of 5. We're missing 2, so those are our complex. So I normally subtract 2 from the negatives, but can we take 2 away from our 1? No. So since I can't take 2 away from the 1, I move over to the positives. Take a set of 2 away from it. So we go from 4 to 2. So then we have 2 positives. Since the most negatives is 1, we have 2 and 1. Yes? And at this point here, I would repeat the process. I would try to take 2 away from the negatives till I can't anymore, but we already can't. So then I switch back over to the positives, take 2 away, and do this here. So the way that I look at it is I keep taking 2 away from the negatives till we can't anymore and reset. Because our total possible positives was 4, 2, and 0, yes? Another way to look at it is we're matching up every positive with every possible negative, putting them together in their pairs. So we can have 4 and 1, 2 and 1, 0 and 1. We have those listed there. And then our complex are 0, because then we got to add them together and see what we're missing. Does that make sense? Because if, I'm going to say that we had 3 and 1, so we'll just say the degree is 7. We'd have to do all the combinations, so 4 and 3 and 4 and 1. 2 and 4, or 2 and 3, 2 and 1. 1 and 3, 1 and 1. We have to combine them all. We have to see every possible arrangement. And the easiest way I've seen to find all the arrangements is I would start out with the most of each. So here, 4 and 3. And I keep taking 2 away from the negatives till I can't anymore. Reset it back to the top, take 2 away from the positives. So really what I'm doing is 4, 4 and 1, 4 and 2. I keep connecting all the ones with positives. And when I can't anymore, I move to the next one. And then do the process again. I connect all the combinations one at a time. And that's just how I arrange it. Does that make sense? So it's one of those things, there's a lot to it and not a lot to it all at the same time, if that makes sense. But what we're looking for in the end is this chart. Does that make sense? Okay. Any other questions on our Descartes rule of signs? Positive, negatives, and complex. No, the synthetic division when dividing by a quadratic is. Huh? We did that yesterday. Yep. You know what? So I think solving does finish this up. Okay. Do we need to see another example of Descartes' rule of signs? Yes or no? Yep. All right. Yeah. So let's move on to solving for those who do have trouble with Descartes' rule of signs. If you do have a chance to come back in here, ask questions. Awesome. I will also be here till the basketball game, so I'm not going anywhere anytime fast. Solving. Solving, all of the solving ones, I will tell you this here. First thing to do is graph them. First thing to do is graph them. goes y equals. So if we have the first one, x to the fifth minus 20 x to the third plus 20 x squared minus 21x plus 20. Now, since the degree is 5, we should have how many solutions? 5. We are going to find at least 3 by graphing. Every single one of the ones that we have on the test will give us enough solutions to get it down to a quadratic. You can hit enter, then graph, but we have the graph here. We can go second graph. So 4, 1, -5. So the 3 zeros we had so far is -5, 1, and 4. Bless you. Bless you. We want y to be 0. Now, it is possible for x to be 0 also, but that's if it crosses at the origin. X and y are 0. We're more focused on the y value. We're looking for what value of x will make y be 0. Y is the one we want to be 0. Now, since we did not get all of them, we're going to do synthetic division to get it down to a quadratic and then solve from there. Here we're going to go through the division part. -5 times 1 is -5. 0 plus -5 is -5. -5 times -5, negative times a negative is a positive. 5 times 5 is 25. -20 plus 25 is +5. -5 times +5 is -25. 20 plus -25 is -5. -5 times -5 is, it's just 25. I was about to say that's going to make everything not work. -21 plus 25 is 4. -5 times 4 is 20, which does give us a remainder of 0. Now again, if the calculator told us the y value for each of the given x is 0, the remainder should also be 0. So again, you could do each of the individual steps of this in the calculator, the multiplication, addition, and there's nothing wrong with doing that. Because it does make it easier, it does make it simpler, and it does verify that you are getting the correct calculations. It just takes me longer to do this, switching between the two. Pick 4. Because again, the order in which we do these does not matter. You just need to pick one and do it, and then go from there. So if we do this with 4, 4 times 1 is 4. -5 plus 4 is -1. 4 times -1 is -4. 5 plus -4 is 1. 4 times 1 is 4. -5 plus 4 is -1. 4 times -1 is -4. And 4 plus -4 is 0. And we get this here. Now this point here, this is factorable. So if you watch the 441 video, we could factor it at this point. But I wouldn't, mainly because, do we have another solution?
Yes.
We have 1. So 1 times 1 is 1. -1 plus 1 is 1 times 0 is 1 plus 0 is 1. 1 times 1 is -1 plus 1 is 0. Remainder, constant term, x and x squared. Equals 0. Now, if there's not a middle term, if there is no middle term, there's not a term with x, get the x squared by itself. So we subtract 1 first, telling us x squared is -1. At this point here, we can square both sides because the square root and square will cancel, telling us it is x. Whenever we take the square root of both sides, we have to add the plus or minus. Square root of -1 is I. So our solutions are plus or minus I, -5, 1, and that gives us 5 because our -1, or -5, 1, and 4 is 3. Our positive I and negative I give us a total of 5. Questions on this here? Now looking at this here, how many solutions we should have is 5, yes? Just by graphing, we got how many? So even if I get stuck, even if you get stuck, you can at least get 3 out of 5. 3 out of 5. So even if you get stuck, at least list the ones you can get by graphing. Where at minimum it'll be like the last one. Yes. There are some where there are repeated zeros, so there's chances we can repeat them. So there are those. Yeah, or 0 3 times or stuff like that. So 30, 31, 32, 33, or 34. Which one do we want to look at next? 32. 32. One thing I will tell you is if we ever look at a formula or a polynomial, higher degree polynomial function, and there is no constant term, one of the zeros is 0. And interestingly enough, whatever the degree of the smallest variable is, actually tells us how many zeros show up. So what's the smallest variable? 3. So it actually works out 0 works 3 times. Because again, we're trying to find out what value of x will make this thing be 0, yes? If there's no constant term, a number without a variable, I can plug 0 in and it's going to cancel everything out, yes? And the degree or the exponent, the smallest exponent attached to the variable, tells us how many times it's going to repeat itself. Works out to be 3 times. Because really, greatest common factor between these two is, well, we do have a number. But if we're looking purely at the variable, we would factor m out of it 3 times, yes? That'd be multiplied out front. But if I set this up for the division, not so much the number of the cubbyhole, we'd have 9 for x to the 5th, 0 for x to the 4th, -27 for x to the 3rd, yes? X squared, or m squared would be 0. M, constant. How many zeros do we have out there to the right? 3. I'm going to do 0 once. Well, I would, yeah. Give y'all a second to copy that down. And the only thing nicer than doing synthetic division with 1 in the cubbyhole is 0. Because 0 times 9 is 0 plus 0. 0 times 0. -27 plus 0. Yeah, -27. 0 times -27 is 0 plus 0. 0 times 0. 0 plus 0. 0 times 0. And lastly, 0 plus 0. Well, we're going to do 0 again because we can try this again. 0 times 9 is 0. 0 plus 0 is 0. 0 times 0 is 0. -27 plus 0 is 7. 0 times -27 is 0. 0 plus 0 is 0. 0 times 0 is 0. And 0 plus 0 is 0.
Let's go.
0 times 9 is 0. 0 plus 0 is 0. 0 times 0 is 0. Negative 27, 0, 0. Now, we never plugged this into the graphing calculator, did we? Well, we could plug the original one in. Now, at this point here, if I plug it back in, this is a remainder, term without x, term with x, term with x squared. So what we're left with is x squared, sorry, 9x squared minus 27. We have this here. Well, that's helpful and not helpful all at the same time because, well, those are not nice numbers. But, yes. Well, I'm realizing I was not supposed to use x, but it doesn't really matter. Yeah, it's still the variable. It's still going to give us the same result. Because it's supposed to be m, not x, but yeah. At this point, we're very much used to using x, and if you switch between m and x or whatever the variable is an x, I'm not counting off. Then indeed we would. So our m squared, 3. Square root of m is m, plus or minus. Square root of 3 is a square root of 3. Because it would only become the square, or I squared of 3 if the 3 had been negative. Yep. Comes if we have the square root of a negative. Yeah. Questions on this here? Any other ones that we want to look at? So we good with solving? Yes. Because here, x to the 4th, I'm going to go on and just graph it. And then I'll answer your question here. I'm looking at number 30. So number 30, x to the 4th minus 6x cubed plus 7x squared plus 6x minus 8. The degree is 4, so there should be second table. Negative 1, 1, 2, and 4. That's a total of 4 values of x that make the y value be 0. We're done. The graphing calculator gave us 4 solutions. The degree is 4. The number of solutions we need is 4. We have 4, so we are. Any questions on any other part of this test? Question? I do not remember, but you should, especially solving all these here. Go back over it. Anything you were feeling a little hazy on, go back over it, review over it. You should be able to finish this in a day.
That's the only thing that I was a bit.
Yeah, especially with the solving. start with the graphing and then go from there. Yes. Descartes' rule of sign here. So 7 to the 5th, it changes. 5th to the 4th, changes. 4th to 3rd, changes. Does not change. Change and change. So the number of positive zeros is 5 or 2 less than it. So we could say 5, 3, 1. Because, I mean, we could write those down. We'll also write them down in the table. Because if listing them out does help, then I would list them out. Now our negative case, we're looking at, say, g of negative x. Or really, we're just going through, if the exponent's odd, we change the sign. If the exponent's even, it stays the same. So our 6x to the 7th is odd, so it becomes negative. So then the next one's negative, an odd power, so it becomes positive. The next one's even, so it stays the same. The next one is odd, so it's going to change from negative to positive. The next one's even, so it stays negative. The next one is odd, because it is to the first power, so it would change and stays the same. And now we're going to count the signs. First one's negative to positive, so that's 1. Positive to positive, so no. Positive to positive, no. Positive to negative is 2. Negative to negative, no. Negative to negative. We can't have 0. We just can't have a negative amount. It's almost the same as kind of objects, physical objects. I could have 2 drinks or I could have 0 drinks. I can't have negative 2 drinks. I mean, if we start thinking more in the relative realm of negative 2 as being you owing, but we're not going to think of it in that case. Now at this point here, what we're doing, I wouldn't necessarily write this because it'd be a whole bunch of arrows, is that we're going to have 5 and 0, 3 and 0, 1 and 0. We're doing every possible combination. Instead of trying to keep track of all that, what I do is this here. And I always start with the most of each. And what I'm doing with the minusing 2 is that I'm connecting every positive with every possible negative combination. And the first one we can have is 5 and 2. Well, the total needs to be 7. Well, 5 plus 2 is 7, so we don't need any complex. 5 and 0. So we're missing 2. Now I can't take 2 away from the negatives anymore. There's no other possible negative set. So we reset it back to the highest amount, 2, and take 1 away from the positives. 1 set of 2 away from the positives. Now we're going to do every combination of 3 and negatives. But before we do that, 3 plus 2 is. So we're missing 2 to give us our 7. And then we can have 3 and 0, which means we're missing 4. Can't remove any more from the negative, so we reset it back to 2, take 2 away from the positives. So we're going to have 1 and 2, which is a total of 3, which means we're missing 4. And then I repeat the process. We'll take 2 away from the negatives, have 1 and 0, which means we're missing 6. Can I take 2 away from the negatives anymore? Can I take 2 away from the positives? You're welcome.